Hi, I'm Karen Savage, and I'd like to welcome you to a video series on flood resiliency in British Columbia. I would like to start by acknowledging that this video is being filmed on the traditional and unceded territories of the Musqueam, Squamish, and Tsleil-Waututh peoples. Along with my colleague Diane Meehan, I am co-author of BC Housing's Builder Guide to Site and Foundation Drainage. We have worked with BC Housing and a multidisciplinary team in order to compile and develop flood resiliency recommendations to inform the building industry in British Columbia. These recommendations can be found at the link provided in the video description. We are pleased to present this video series educating British Columbians on flood risk mitigation measures. This series of recordings is part of BC Housing's Mobilizing Building Adaptation and Resilience Initiative, or MBAR. MBAR promotes designing for resiliency of buildings against natural disasters such as flooding, earthquakes, and wildfire. This video series will offer solutions for various types of developments at risk of flooding, including single-family residences, existing multifamily or strata developments, and new construction. This video is the fourth in the series and will give an overview of understanding the different flood risks for new buildings, including commercial, multifamily, and mixed-use developments. This video offers strategies for members of the project team to consider during the design, permitting, and construction phases of these developments. For information on existing single and multifamily buildings, including an introductory video providing background on flooding and site-specific risk, please refer to the first through third videos in this series. In general, the business case for climate change resiliency is to protect your investments and proactively plan. You can streamline future operations and upgrades if you have a clear understanding of the potential risks for different properties. Additionally, suitable planning can protect tenants and occupants and limit the loss of rental income following an extreme event. You can also advertise this resiliency to prospective tenants or buyers as a value proposition of your development. Flooding occurs when water flows into or collects in a location where it is not expected or accounted for in the design. Understanding, managing, and mitigating flood risk is important to protect our homes, property, and investments. As we have seen, the climate is changing, and this will increase flood risk. However, by following best practice flood resiliency measures, including those described following, we can limit damage from flood events. Common types of flooding include overland flooding, pipe backup, and groundwater flooding. Overland flooding can originate from rivers and lakes or from the ocean, including from king or extremely high tides in combination with storm events. Alternatively, rainfall or pluvial flooding can result if a rainfall event overwhelms catch basins, drainage ditches, and other diversion or water management features, and this water flows over the ground into a building. Pipe backup can occur when the pipes in and around a building, including for drainage, storm and sanitary sewers, or water pipes, fail to function as designed. This may occur due to a failure of the pumps, if present, a break in the pipe, or when the capacity of the system is overwhelmed, on your property or on adjacent properties. Pumps can fail due to faulty triggering of backup generators during a power outage, or due to flows which exceed the pump capacity during an extreme event. When pipes become overloaded with water, the water may back up into a building and cause damage. Finally, groundwater flooding occurs when the groundwater beneath your property is higher than the building can accommodate, and it enters the interior of the building, including through capillary action or wicking up, or through cracks or gaps in the slab-on-grade or perimeter foundation walls of the underground structure. It's important to understand that floodwaters will be contaminated with harmful substances and can be vectors for disease. The flood construction level, or FCL, for a new project should be established by suitably qualified professionals. The FCL is not the high water level established by a surveyor and may be different from the Q200 level. To determine the FCL for a particular site, suitably qualified professionals consider site-specific parameters which may include factors such as the site location and elevation, tidal elevations, wave run-up, whether community protection is in place, and freeboard, amongst others. The FCL should be expected to rise due to climate change. In general, all habitable spaces should be located above the FCL. Parking is often allowed beneath the FCL, but the safe exit of vehicle occupants from these parking areas should be allowed for. Finished basements are typically not allowed beneath the FCL unless the basement is tanked. To put flooding in perspective, it might be helpful to compare the current BC standards for society's acceptance of flooding versus that of seismic risks. Based on current standards, our society accepts that a building should not collapse for a seismic event with a 1 in 2475-year return period, which is estimated to have about a 2% chance of occurring over a 50-year building design life. Comparatively, our acceptance of flooding is much greater. Although it varies, the typical design standard for properties at risk of coastal or inland flooding in BC is that a building will not flood for a 1 in 200-year design event, which is estimated to have about a 22% chance of occurring over a 50-year building design life. Although the risks and safety considerations associated with these two types of hazards are different, the relative expected frequency of flooding events in our province indicates how important it is to develop resiliency against these events. In order to protect developments that are proposed in areas where flooding can occur, the project team should plan for failure. For example, they should assess the impact of different failure scenarios associated with power outages, pump failure, sewer capacities being exceeded, backflow valve seizing, etc. In areas prone to flooding, it should be expected that water will enter the building at some point in the future, and the effect of this should be accounted for in the design. The design should be modified to reduce the impact of this future flooding and to allow for efficient cleanup. Where passive systems such as self-rising flood barriers are used, manual backup should be provided. As the design team considers ways to reduce the impact of future flooding and to allow efficient cleanup, decisions will be made on how to manage risks. In order to document these design decisions and to inform future planning, this information could be enshrined in a design philosophy statement. This could go on title for a particular property, to be used as a time capsule message from the current design team to a future design team that may be involved with design upgrades to a building or with remediation following a flood event. The design philosophy statement could summarize key design parameters, decisions, construction methodologies, design lives of key components of the facility, and the building code and FCL at the time of permitting for a particular project into one short document. Decisions around whether the building was protected by conventional damp proofing or waterproofing, or whether it was designed as a tanked structure, should be outlined. Additionally, it is noted that building codes are often issued in December of a given year, and thus the previous code might govern a design for buildings permitted or constructed around the time of a code change. This is important for future design teams to appreciate. Integrating flood resilience strategies into commercial asset management plans and long-term financial planning protects owners, investments, occupants, and communities. The owner should obtain appropriate insurance coverage to allow for replacing damaged components or building back better. They could consider maintaining a mortgage-free asset in a low-risk area to provide interim financing for repairs of buildings that may be affected due to flooding or other natural hazards. This would be expected to expedite repairs and return of rental income. It is also important that regular maintenance of building systems be carried out. This would include maintenance of below-grade building systems which are often out of sight and out of mind. As part of the regular maintenance, triggering of the backup power supply for pumps should be tested. It would likely be appropriate to enhance this emergency power with battery systems to bridge the time it takes to activate a generator. As building components age and become obsolete, the design life of the component expires, or future risks increase. Carrying out upgrades to the building systems and other elements would become increasingly important. If a site is in an area where flooding could be expected, education materials could be prepared for the residents. This could include references to local flood forecasting and warning systems, and a list of supplies which each resident should have on hand. The design team and owner for a new development in an area prone to flooding or other natural hazard should also consider where and how sheltering in place would be implemented during an emergency. All the professional disciplines represented on a project team should understand flood-resilient design objectives. They should understand the hazards and the risks associated with flooding and the design life and importance of the building when assessing resiliency targets. The project team should make design and construction decisions that balance construction costs and insurance premiums, operation costs, and future repair costs. Priority should go to adopting low-cost, high-impact measures to increase flood resiliency. The design should build in opportunities for future upgrades as risks and technologies change. We will now share some discipline-specific recommendations for the design team which you can share with your colleagues. Timestamps for each discipline are included in the video description. For new developments, the coordinating registered professional is usually the architect. The role of the CRP is to coordinate the design work and field reviews of other consultants required for the project in order to ascertain that the design will substantially comply with the BC Building Code or Vancouver Building Bylaw and other applicable enactments respecting safety. The CRP may be the most suitable member of the project team to establish resiliency targets with the owner. The CRP should compile a list of all the openings at or near the flood construction level, which could serve as shortcuts for floodwaters to enter and move within the building, and which may require raising or retrofitting in the future, and these features should be listed in the design philosophy statement. These openings could include parkade vent shafts, soil gas vents, landscaping drains through the podium, electrical and telecommunications conduits from outside of the building, etc. The CRP should consider ways to delay floodwaters, which could include sealing of access points near or below the FCL and utilization of curbs at strategic locations above adjacent street grades. Access points that lead to life safety issues, such as a flash flood in the parkade, should be proactively addressed. It is important to realize that as exterior water levels rise during a flood, these access points will be more at risk of being overtopped. If and when this overtopping occurs, water will continue to enter the structure below the exterior water level until the interior water level matches the exterior and the underground structure is entirely full of water. At areas with a large access point, such as a parkade ramp, this can result in a flash flood when the ramp is overtopped by floodwaters, as shown in the video here. Warning signage or flashing lights could be provided at parkade entries when moisture sensors in the parkade are activated. The CRP should also consider potential cascade failures that could include fire or loss of power due to a flood due to a seismic event, and closure or dysfunction of municipal infrastructure, including roads, sanitation, solid waste, and the compromising of the quality of potable water during a flood event. Vent shafts are an access point for floodwaters which could be harnessed as a flood protection measure. Specifically, they could serve as emergency exit points for people that may otherwise be trapped in a flooding parkade. In addition, vent shafts that are located around the exterior of the building could be equipped with a deep sump that would allow for dewatering of a flooded parkade. In the event of a flood, pumps could be lowered directly into this deep sump, or the sump could be proactively provided with pumps. In either case, this would lead to more efficient removal of floodwaters than might otherwise occur if pump hoses are required to be long enough to wind down many levels of the parkade. There are many other features that could be incorporated into a building design to improve the overall building resilience, including for occupants in times of emergency. We encourage design teams to be forward-thinking and consider how emerging technology could be used to enhance buildings now and into the future. One way to improve the resiliency of a building that has a shared amenity room or party room could be to enhance this area to provide for some basic needs during an emergency such as a flood or prolonged power outage. These amenities could include solar-powered charging outlets for residents to charge their phones, a refrigerator for food storage, basic cooking implements, bathrooms with capacity to store water and wastewater in the case that sewers are full and not functioning, and other necessities. Flood-resilient design for architects on a project team could include specifying that electrical outlets be elevated and specifying mold and decay-resistant materials such as tile or concrete instead of carpet, steel or blue wood instead of timber studs, and blue board rather than drywall in areas that may be prone to flooding. The team led by the architect should determine if and where hydrostatic forces could develop on interior walls during a flood event. In the below-grade areas, openings such as the tops of window wells, exterior rim elevations for vent shafts, door thresholds, and the crown of the parkade ramp should be elevated above the flood construction level. Although the finished floor elevations of the parkade slab on grade would slope towards interior catch basins, architectural reveals, which may be installed as control joints, could also serve to drain floodwaters toward the deep building sump. Structural design of a tanked structure should account for buoyancy both during construction and in the permanent condition. In general, tie-down anchors to resist buoyancy may not be recommended as these create penetrations which compromise the below-grade building envelope. Additionally, they may lose resistance during a seismic event. The below-grade structure of the building should be designed to resist external pressures, which commonly include lateral earth pressures, hydrostatic pressures, seismic earth pressures, and pressures due to adjacent surcharge loads. The geotechnical engineer is responsible for specifying the maximum design groundwater elevation for a new development, and that elevation should take into account seasonal and tidal effects and include for some freeboard in consideration of year-to-year variability. Where this parameter is critical to the building design, a generous freeboard should be provided due to the sparseness of available longitudinal groundwater monitoring data. The maximum design groundwater elevation in relation to estimated return periods could be correlated with precipitation events. If a building is designed with foundation drainage that relies on an exterior groundwater management strategy, such as a continuous secant pile wall or sheet pile wall, to minimize groundwater infiltration, the seismic performance of that structure should be checked with respect to the potential triggering of a flood event. It is expected that movement of greater than about 2 inches of such a groundwater cutoff wall during a seismic event could result in structural damage of sufficient magnitude so as to cause a breach, which could lead to significant groundwater ingress. The designer of this system should specify the maximum expected deformation that could occur without breach of the structure. Peak ground accelerations should be used to estimate seismic earth pressures and the resulting wall deformation. Seismic data is available for a 1 in 475-year event and a 1 in 2475-year event. Therefore, it may be appropriate for a design team to consider the seismic performance of a groundwater cutoff wall during a 1 in 475-year event in assessing the flood protection it would provide to a below-grade parkade from flooding. It is expected that if this wall is internally braced by the below-grade building slabs, this deformation could be optimally limited. The geotechnical engineer should also consider the possibility for hydrostatic pressures developing between a secant pile wall or other groundwater management structure and the building foundation wall, and what mitigation measures might be required. In floodplain areas which are generally underlain by compressible soil, temporary dewatering systems employed in order to allow construction of a below-grade structure can induce settlement of adjacent property due to the lowering of the groundwater table, as shown in these before and after photographs of a residence adjacent to a new development. The geotechnical engineer for a project underlain by compressible soils and a high groundwater table should be sure to communicate these risks to the rest of the project team and to the development owner. Owners are reminded that they are responsible to ensure that Sentence 4.2.4.9 of the BC Building Code or Vancouver Bylaw is followed. This states that where proposed construction will result in a temporary or permanent change in the groundwater level, the effects of this change on adjacent buildings shall be fully investigated and provided for in the design. At development sites bordered by rivers and creeks, the geotechnical engineer should also consider the potential for scour due to extreme water flows and coordinate with a hydrotechnical engineer to obtain a suitable design scour depth in order to protect foundations from loss of subgrade and bearing. With respect to above-grade structural design, it's recommended that a hydrotechnical engineer or geomorphologist with appropriate expertise be included on the project team. These experts can advise on hydrodynamic loads due to the impact of debris launched by wave forces that might manifest. In a floodplain, buildings will have habitable areas above the flood construction level, and adjacent exterior landscaping is expected to also be near this level to facilitate access. However, the podium slab supporting this landscaping could be below the flood construction level. Therefore, the weight of water in a flood condition on this podium slab should be allowed for by the structural engineer in their design of the slab. The hydrotechnical engineer should be viewed as the flood expert on the project team and is typically responsible for determining the flood construction level for a development. This consultant could also advise on the flood events of greater magnitude that the building may benefit from being designed to be resilient against. The hydrotechnical engineer should also support the project team in determining other flood-related risks and design parameters, potentially including hydrodynamic loads, and could work with owners and the CRP to establish risk tolerance levels and resiliency targets. The building envelope engineer should also consider flood-resilient design strategies that affect the podium slab, especially below the flood construction level. This includes the damp-proofing or waterproofing membranes used, how those membranes may be lapped and terminated, and how those membranes and laps and terminations will perform when subject to a few feet of water head. As floodwaters surround the building, additional protection may be offered if a podium slab is provided with a concrete curb at its perimeter to limit the risk of floodwaters entering the base courses of the podium, especially if the podium slab includes landscape drains that would penetrate the structure. Material durability and integrity of building envelope products should also be reviewed. The building envelope engineer should also ensure that all mechanical, electrical, or other penetrations through the building envelope that are near or below the flood construction level are suitably sealed against water entering the building. Mechanical engineers should review the functionality of mechanical systems during flood events. This could include assessing whether pumping of plumbing fixtures below a critical elevation is prudent, and specification of backflow valves for both storm and sanitary sewer pipes. Where normally open backflow valves are required, inclined flapper valves or other proprietary solutions could be used. In the event of municipal sewers being full of floodwaters, consideration can be given to regulating water to suites and restricting flushing of toilets or allowing for alternate sewage storage, for example, possibly repurposing the stormwater tank, as this could limit backups within the building. Alternatively, these recommendations could be provided in an education package for residents, which details appropriate use of plumbing fixtures during an emergency. A mechanical engineer may be involved with the design of a perimeter drainage system, which is in use to offer protection against buoyancy during construction of a below-grade tanked structure. The mechanical consultant is encouraged to ensure that such a system is decommissioned when the weight of the building is sufficient to resist the buoyant forces, so that the building's stormwater management is not overwhelmed with unintended volumes of water when it is commissioned after construction. However, such a system could be left in place and recommissioned in the future to allow for maintenance of the below-grade envelope. Electrical engineers and elevator designers working on a project in a floodplain should consult the Engineers and Geoscientists BC Practice Advisory, Electrical Engineering Considerations and Flood Resilient Design of Buildings, published in December 2020. In it, recommendations can be found for safe design and operating constraints for elevators and electrical infrastructure in a building which could be expected to be subject to flooding. It is recommended that the design allow for safe shutdown of an elevator at or above the main floor during a flood, and that the elevator not be allowed to descend into a flooded parkade. The main electrical service and elevator machine rooms should be located above the flood construction level, as should electrical panels for services that are located above this level. Many projects are now citing elevator machine rooms on the roof of the building. It is recommended that a moisture or water sensor be included in the elevator pit, which sounds an alarm or otherwise notifies building residents that the elevator pit is flooded. This sensor should be monitored and provided with a battery backup and should trigger the elevator to not descend below the flood construction level. However, consultants could allow for safe operation of an elevator to service the floors above the flood construction level during a flood event. The elevator should be equipped with communication to enable trapped individuals to reach out for help in the event that the elevator phone fails. This could include a cell phone signal booster in the elevator shaft or emergency backup communication to a PA system such as a local wireless system with battery backup power. Monitored occupancy sensors with battery backup could also be provided. The amenity room could be designed to become a hub of the building for residents who choose to shelter in place. Emergency power may be limited to only this location in the building, and the availability of an ongoing power supply would become important for people to be able to charge their cell phones. Electrical engineers could consider photovoltaics and/or thermal solar as passive backup power systems. If such systems will be relied upon in an emergency scenario, daily use in select areas is recommended as a check that these systems remain functional. This could also contribute to cost recovery. Maintaining electrical service during an emergency is important, and triggering of emergency power systems can take a lot longer than anyone would wish. It's therefore recommended that at least 1.5 hours of battery backup be provided to cover the time when the generator is being manually started. And of course, safe reconnection back to the grid should be allowed for in the electrical design. The annuli between conduits and cables in below-grade utilities, including communication infrastructure, should be sealed, and the possibility that T-drains could act as an entrance for water to the below-grade building should be reviewed. Preferably, penetrations through the building envelope for electrical and communications as well as other utilities would be above the flood construction level. With respect to the environmental engineer on a project team, they should review the impacts of changing the groundwater regime, either by constructing a groundwater cutoff structure which would essentially function as a dam in the middle of an area, or by pumping and dewatering a site. Contaminants can be transported with groundwater flow if they are water soluble. Therefore, an excavation advance near an area of environmental contamination could draw those contaminants towards the excavation if pumping is carried out, especially for an extended period of time. Conversely, installation of a groundwater management structure, often optimistically referred to as a groundwater cutoff structure, could deflect the flow of a contamination plume around a site and thus towards other sites. Both of these activities could have a negative impact on the quality of soil and groundwater below neighboring buildings that are not the development site and are not the polluter site. This puts the developer at risk. The robustness of building envelope products used in the vicinity of environmental contamination or salt water should be reviewed, and information in this regard should be shared by the environmental consultant with the building envelope consultant on the project team. Finally, landscaping design should also be subject to resiliency efforts. Of course, the final grading of a building should slope down and away from it, per the BC Building Code. When off-site flooding subjects a development to flood risk, the use of flood walls to redirect floodwaters can be a means of limiting site flooding. Conversely, strategically located swales and drains can be effective in increasing the efficiency of site cleanup following a flood. The reparability of landscaping features following a flood should be considered. As climate change increases both the duration and intensity of precipitation and drought events, selection of appropriately resilient plant species becomes an asset to the project. Additionally, the permeabilities of base courses and drainage layers for landscaping elements should be evaluated, as these can be hydraulic connections for floodwaters. For an in-depth understanding of potential hydraulic connections and other drainage considerations, please refer to BC Housing's Site and Foundation Drainage Guideline. We hope that this video has offered you new insights related to flood risks and planning for flood-resilient communities and homes, and that you will join us in future videos.